Hello scientists, and welcome to this video about ionic and covalent compounds. We're going to talk about how they're formed and also their properties. Before you get started, you need two things. You need this lesson 7 notes handout so you can fill in the blanks, and you are going to need your periodic table. So pause the video if you need to get those two things. So earlier in the course we learned about how pure substances can be either elements or compounds, and we've talked a lot about elements, the ones that you find on the periodic table, but today we're going to talk about compounds. All the compounds that exist on Earth are built from elements. There are 118 elements on the periodic table, but only 80 of them commonly form compounds. There's about 10 million known compounds, but there's billions of possible ones. So known means these are ones that we've been able to find and identify in nature or in the lab, and there's more out there that might be able to be made. So for example, here is hydrogen, which is a gas, and here is carbon. Carbon can form a few different solids like diamonds, but this one is one called graphite. Putting hydrogen and carbon together can result in tons and tons and tons of different compounds. So you can find what's called hydrocarbons, because hydrogen and carbon. You can find hydrocarbon compounds in fruit and vegetable, actually in every living thing. You can find it in candles. The candle wax is a hydrocarbon. You can find it in things like, this is a welder's torch, so it uses gas like the Bunsen burners in our lab. And of course, you can also find it in fossil fuels, like the ones we put in our cars. So hydrogen and carbon can be put together into tons of different compounds, and that's just two of the elements. So we're going to talk about two different kinds of compounds, ionic and covalent. The first one is ionic, and as you might guess from the name, ionic compounds are made of oppositely charged ions. So these the blue text with an underline is where you need to write things down on your sheet. If you need to pause it to do that, that's a-okay, you can pause it. So like the name suggests, ions are a key feature of ionic compounds. They're held together with ionic bonds, which is a strong attraction between oppositely charged ions. So just like magnets, if you have the positive end of a magnet and the negative end, they are attracted, opposites attract. Same with ions. The positive ion and the negative ion are going to be attracted together. And ionic bonds are very strong, hard to break. We're going to be studying binary ionic compounds. Binary means two, so just like the computer language, binary is zeros and ones, or bi means two, like bicycle is two wheels. So binary ionic compounds contain two elements, and this part's really important. One metal and one nonmetal, always a metal and a nonmetal. The metal atom gives electrons to nonmetal atoms, and this results in the formation of ions that have full valence shells. So remember that a full valence shell makes an ion more stable. So we're going to draw an example of an ionic compound. So we're going to do sodium chloride, which is table salt. So a sodium atom transfers one electron to a chlorine atom, and then that makes the sodium atom become a positive ion, Na+, and a chlorine atom becomes a negative ion, Cl-. So grab your periodic table, and we're going to draw a Bohr diagram together. So find sodium. Sodium's number 11, and its symbol is Na. Please excuse my trackpad drawing. There we go. How many electrons does an atom of sodium have? Remember, an atom has the same number of protons and electrons. And sodium has 11 protons because of its atomic number. So an atom also has 11 electrons. So first ones go here, 1, 2. The next ones in the second shell, 3, 4, 5, 6. Remember, the first 4 are unpaired. 7, 8, 9, 10. Like you wouldn't go on the bus seat right next to the only other person on the bus. So 10, and I needed 11. So 1 in the third shell. There's my sodium. Chlorine is 17. Whew, here we go. Cl. So 1, I'm just going to draw lines instead of dots because it'll be faster. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, so the important part here is that you have 1, 2, 3, 4, 5, 6 valence electrons that are in pairs and 1 that's not paired. So now sodium wants a full outside shell, and the easiest way for it to do that is to get rid of this electron. Okay, so I'm actually just going to erase that electron. It is going over to join chlorine over here. Now chlorine has a full shell. Everyone's happy. And remember, you have to put brackets, square brackets, around your ions with its charge. So sodium lost 1 negative electron, so it is positive. Chlorine gained 1 negative electron, so it's negative. Okay, if you're ever not sure what charge it should be, just look on your periodic table. That one has a 1 plus. Chlorine all the way over here has, oops, sorry, there, a negative. Okay, so that is an example of an ionic compound as a Bohr diagram. Structures of ionic compounds. So ionic compounds consist of positive and negative ions arranged in regular repeating patterns called lattices. And this is what this looks like. So here's sodium chloride. The purple circles are sodium ions. The chlorine, remember when non-metals become ions, they get an IDE ending, so chlorine becomes chloride. So the green circles are chloride, and they are alternating. So this is a pattern, sodium and chloride, ions arranged in a repeating pattern. This makes up these little squares. If you looked at salt under a very powerful microscope, you'd see those little squares. And yeah, these are salt crystals. Because ionic compounds are so strong, they have a high melting point. Melting requires breaking ionic bonds, the strong forces holding the ions together in that lattice structure. So a large amount of energy is required to break them apart, and that energy is heat energy in the case of a melting point. So for example, the temperature where sodium chloride begins to melt is 801 degrees Celsius. So you got to heat your salt up super duper hot. That's way hotter than my oven gets, to break apart the sodium and the chlorine ions. Ionic compounds also are very hard and brittle. So this means that if you smash them with a hammer, they're going to break. Ionic solids are hard because ionic bonds are very strong. And when you apply enough force, ions shift. So if here's your crystal, your lattice, if you hit it with a hammer, you're actually going to move those positive ions closer together. And just again, like with magnets, if you have two positives, they repel each other. So it results in repulsive forces that break that solid apart. Okay, that's what brittle means, easy to break. Ionic compounds also conduct electric current, either when they're in liquid or they're dissolved. So we're going to learn about electricity a lot in our next unit, but for now it's just the flow of charged particles, so electrons moving through something. Ionic compounds in their solid form don't conduct electric current because the ions are held closely together. So if you tried to run electricity through salt grains, like what comes out of your salt shaker, it wouldn't work. However, if you dissolve salt or you have an ionic compound that's a liquid, the ions can move around. So those chloride ions that are negatives can move around, so can the sodium, and they can help electrons move from one side to the other. So I'm going to show you a picture. So here's the diagram showing just that. So if you have water, it doesn't conduct electricity. That light bulb's not going to light up. If you just have a cube of salt, it also isn't going to let any charged particles flow. However, if you dissolve the salt in solution, that means you take salt, you put it in water, and you stir it. Now the negatives can move to one side, the positives can move to the other side, charged particles can flow, and our light bulb will light up. Pretty cool, right? Okay, the other type of compound is covalent compounds. Covalent compounds are made of molecules. We've learned this word molecule before, but it's important to know that molecules only apply to covalent compounds. So a covalent bond is a strong attraction between atoms that form when atoms share electrons, share valence electrons. And this is really important. This only happens between two non-metals. No metals involved here. Ionic compound is a metal and a non-metal. Covalent compound is two non-metals. So covalent compounds are made of molecules. And again, a reminder that a molecule is a particle made up of two or more neutral atoms stuck together with a covalent bond. So a covalent bond is kind of like a tug of war. Each team is an atom. So here, say, we're going to, if we talk about water, this could be an oxygen, this could be a hydrogen. Each team tries to pull the rope, which is electrons, towards themselves, but neither side wins. So the bond is the rope that connects them. This is an equally matched tug of war game. Okay, so oxygen and hydrogen in this case would be, there'd be some shared electrons in the middle. They're both pulling on them, but they both pull equally strongly. So the oxygen and hydrogen, neither of them wins. It's just that those electrons are suspended between them and connecting them. So how does this help us achieve stability? So this is water. Here's oxygen and two hydrogens. Covalent bonds form when a single pair of shared electrons is shared between atoms. So each atom contributes one electron to the shared pair of electrons. So here's oxygen. The red one is from oxygen. The blue one's from hydrogen. Now hydrogen atoms have a full valence shell of 2 electrons. And oxygen atoms have a full valence shell because they have 8. So both of these are happy now. Wow, all 3 of them are happy now. Okay, they all have a full shell. They're sharing. Isn't that nice? Okay, I want you to pause the video here and try to fill in these blanks. These are 3 different ways that atoms can become stable. So pause the video, come back when you're ready. Welcome back. So let's see, did you get it? Metal atoms can lose electrons to achieve a full valence shell. Non-metal atoms can gain electrons to achieve a full valence shell, and non-metal atoms can share electrons with other non-metal atoms to achieve a full valence shell. So 3 different ways we can get stability here by making compounds. So last thing to go over here, there are a couple extra slides in your handout. That's okay, they're just there for you to read if you need it. But skip ahead to number 18, properties of covalent compounds. So covalent compounds have low melting points. The forces holding atoms together in a molecule are strong. So these bonds between the hydrogen and oxygen are really strong. However, the bonds attracting the molecules together are very weak. Unlike that crystal lattice structure of the negative and positive ions for an ionic compound, molecules are held together very weakly. So therefore, it doesn't take as much energy to break those molecules apart, and the covalent compounds have a relatively low melting point. 2 more properties of covalent compounds. They're relatively soft. Because there's weak forces between the molecules, it's easier for those molecules to move around relative to each other. So unlike ionic compounds where when you smash it with a hammer, those particles are going to repel each other, that doesn't happen here. If you smash it with a hammer, those molecules are just going to bend, just move around where the hammer is because they're not really connected to each other that strongly. Covalent compounds are also poor conductors. So because there's no charged particles, they do not have free electrons, and they don't conduct electricity very well or heat. So this is why, though here for these wires, The part inside is made of metal, which is a great conductor, but the outside is made of plastic or rubber, which just doesn't conduct electricity that well. Same with if you are going to get something out of the oven, you're going to use a rubber oven glove. Rubber is a covalent compound, and it's a bad conductor of heat and electricity. I hope that makes sense. Thanks for sticking to the end of this video. Let me know if you have any questions next time I see you in class. Have a good day.